Alright, this is section 8.4, Trig identities. Guys, you're going to really need to know the identities from chapter 7. I know I tested you on them on the unit number 1 test. Please look over them before you start trying to do these, because you have to have them memorized to be able to be successful on this section. Alright. When two functions f and g are said to be identically equal, that means that the function of x has to equal g of x for every value of x which both functions are defined. Such an equation is referred to as an identity. An equation is not an identity is called a conditional equation. So identity means that the left-hand side is equal to the right-hand side. What we're going to do here is we're going to prove that the left-hand side is equal to the right-hand side. And we're going to determine which side is more difficult. We're going to start there, and we're going to work our way until both sides look exactly alike. Okay, so the first identity that we saw last chapter was the quotient identities, where tangent theta equals sine over cosine and cotangent theta equals cosine over sine. The next identity that we looked at during the last chapter was the reciprocal identities. So cosecant is defined as 1 over sine, secant is defined as 1 over cosine, and cotangent is defined as 1 over tangent. And then we had the Pythagorean identities. I told you guys to memorize the first one, sine squared plus cosine squared equals 1, and then you could get the other two by dividing by cosine squared. And if you divide the original, sine squared theta plus cosine squared theta equals 1, by cosine squared theta, you would get tangent squared theta plus 1 equals secant squared theta. And then to get the third one, I told you to divide by sine squared theta. So if I divide everything by sine squared theta, I got cotangent squared theta plus 1 equals cosecant squared theta. The other things you have to know are the even-odd identities. So remember, if you have a negative in front of sine, that means that that is an odd function, so the negative comes out. Same with its reciprocal identity, cosecant. The negative comes out in front of cosecant, making theta positive. For cosine and secant, remember those are the even functions. So these are even, which means that when you see a negative in front of theta, it comes out, but it doesn't show up. So it says cosine theta and then regular secant theta. So remember, even means when we have a negative in front of theta inside parentheses, it equals the regular cosine, the regular secant. Okay, odd functions are tangent and cotangent, so that means that the negative has to come out in front of them. Please see chapter 7 for more information on that. I know it went through this really fast, but these are called the fundamental identities. Okay, and to be specific, the fundamental trig identities. Alright, so let's go ahead on to objective 1. This section is going to be a blast from the past. So, remember when you took MAC 1105, when the heck do I use some of this stuff, or why do I have to know it? Now you're going to see why your teacher spent so much time on things like conjugates. So if I have some binomial, let's say a plus b, its conjugate is going to be a minus b. Okay, so an example of that where you'd have to use the conjugate is usually in rationalizing the denominator. So for instance, if you had the square root of 2 plus 1, you'd have to take the conjugate, which is the square root of 2 minus 1, and multiply those together to get rid of a radical. Okay. Difference of perfect squares. I call this dopes. And the difference of perfect squares says if I have my first term is a perfect squared minus the second term, which is a perfect squared. It factors out into a plus b, a minus b. An example of that would be maybe x squared minus 4, which factors out into x plus 2, x minus 2. So difference of perfect square only works on perfect squares. Alright, factoring. So there's a lot of factoring that goes into place. You know, we could have something like x minus 2 quantity squared. That's the actual factors of the trinomial, which is x squared minus 4x plus 4. So that perfect square trinomial yields 2 factors x minus 2 times x minus 2. It's things like that. Once again, difference of perfect squares I showed you. It's just, you know, figuring out factoring. So I'm going to make up another example for you, but I got to work backwards here. So let's say x squared minus 5x plus 6. How does that factor out? X minus 3, x minus 2. Okay, so if you need help factoring, you can either tell me or look at Khan Academy and just type in on YouTube Khan Academy factoring, and there's a lot of examples of how to factor out trinomials, binomials, and using the grouping method. Okay, so now let's get into the nitty-gritty of things. We have 4 parts, and they're asking us to simplify this. This is not quite an identity yet. This is just asking you to simplify by using the rules stipulated. So let's look at A together. It says, show cotangent theta over cosecant theta by rewriting each trigonometric function in terms of sine and cosine functions. Okay, so if we start at the beginning, cotangent theta over cosecant theta, and it tells me I have to write these function ups in terms of sines and cosines. Whoops, sorry guys. Alright, so cotangent. Cotangent is defined as cosine theta over sine theta. And cosecant is 1 over sine theta. Okay, I can't stop there. I have to simplify this down. So I have cosine theta over sine theta times sine theta over 1. If I cross out the sine thetas, because they cancel each other, I'm left with cosecant theta. And that is a simplified version of cotangent theta over cosecant theta. Okay, B says show that cosine theta over 1 plus sine theta is equal to 1 minus sine theta over cosine theta by multiplying the numerator and denominator by 1 minus sine theta. Okay, so if I start on that left-hand side, because that's what the directions are telling me to do, I have cosine theta over 1 plus sine theta. Now it's telling me to multiply that by 1 minus sine theta. And what you do to the bottom, you have to do to the top, because this is like multiplying by 1. So I'm not really hurting the equation, I'm just multiplying by 1. Okay, when I do that, let's take care of the denominator first. This actually becomes the conjugates. And when you have 2 conjugates, this actually becomes the difference of perfect squares. And if you don't believe me, FOIL it out. So you take your first term, you square it. So 1 squared is 1, minus the second term and square it. Sine theta squared. Okay, so this becomes 1 minus sine squared theta. Okay, over cosine theta times 1 minus sine theta. Okay, now I'm not done yet. What I need to do is I need to use Pythagorean identity in the denominator. And the Pythagorean identity, just to remind you, it's sine squared theta plus cosine squared theta equals 1. So if I take sine squared theta over the other side, I get cosine squared theta equals 1 minus sine squared theta. And that's exactly what I have in the denominator. This is exactly what I have. So I can use substitution. So that's exactly what I'm going to do. So in the numerator, I'm going to leave it alone just for now. Okay, in the denominator, I'm going to substitute in wherever I see 1 minus sine squared theta, I'm going to place in cosine squared theta. Alright, so once I got that, now I can simplify this down. I can take out a cosine theta out of both. So I'm left with 1 minus sine theta over cosine theta. And that's exactly what they wanted me to show. So now the left-hand side looks like the right-hand side. Okay, so this is, part B is actually kind of what you have to do when you do an identity. So it's a good warm-up. Alright, let's go ahead and do C and D. And I'm going to do that on the next page so I have some room. Okay, part C asks me to simplify 1 plus sine u over sine u plus cotangent u minus cosine u over cosine u by rewriting the expression over a common denominator. Okay, so what's the common denominator? So if I look at the denominator, I have sine u times cosine u. That's my common denominator. So I'm going to take a moment and I'm going to build up the numerator based off of what I get down in the denominator. So I'm just rewriting both. Okay, so I had 1 plus sine u in the numerator before, and now I have the denominator times cosine u. So what I do to the denominator, I have to do the numerator. And then the second one, I had cotangent u minus cosine u, and I'm going to multiply that by sine u because I did not have that in the denominator before. Okay guys, so let's go ahead and do some distributing and see what we can do with this. Alright, so I'm going to distribute cosine u through 1 plus sine u in the numerator there. So cosine u times 1 is cosine u plus cosine u times sine u. Okay, now I'm moving over to the second fraction, if you will, a rational expression. I get sine u times cotangent u minus sine u times cosine u. Okay, now this is all over sine u, cosine u. Okay, let's see if we can't cancel something out. And I have sine u, cosine u, a negative, and a sine u, cosine u positive, so those two can go away. So now I have cosine u plus sine u times, and I'm going to write this in terms of sines and cosines. So cotangent is defined as cosine u over sine u. And the reason why I'm doing that is because everything else is in sines and cosines. So this is going to allow me to make this look a little bit better because I'm trying to reduce it down. So since I wrote cotangent u as sine u cosine, or cosine u over sine u, I can cancel these two out. So what am I left with? Cosine u plus cosine u all over sine u cosine u. Alright, so now I have 2 cosine u over sine u cosine u. The cosines cancel out. Now I have 2 times 1 over sine u, and this equals 2 cosecant u. So all I did there, just to let you know, is I did a little bit of substitution. Cosine u plus cosine u is 2 cosine u, and sine u times cosine u was in the denominator. That allowed me to get rid of cosine u because sine u is multiplied times cosine u. And then I just brought the 2 out and put it as 1 over sine u. And 1 over sine u, just to remind you, is the reciprocal identity cosecant u. Okay? So all that at the beginning of C basically came down to 2 cosine u. Alright. So your next objective is to actually establish an identity. Now we're getting into the nitty-gritty things. No, excuse me, I forgot to do D. So no, actually we have to do D first. Okay, the directions say to simplify by factoring. Alright, so in the numerator, this is the difference of perfect squares. So if I factor that out, I get sine v plus 1 and sine v minus 1 all over. Now, since both terms in the denominator have a tangent v, I'm going to go ahead and pop that out. And when I take that out, I divide each of my terms by tangent v, and I'm left with sine v minus 1. Okay, at this point, I can cancel sine v minus 1 because those binomials are exactly the same. And I'm left with sine v plus 1 over tangent v. Okay, I can't go that much further now. And the reason why I can't go any further than this is because I have a binomial in the numerator. And even if I turn tangent into sine over cosine, it isn't going to help anything. And to show you what I mean, if I have sine v plus 1 over sine v over cosine v, sine v plus 1 over 1 times cosine v over sine v, I can't cancel these two out. This is a binomial and this is a monomial. You cannot cancel them out. They have to be the same. So if you have a binomial, the only way you can cancel it out is like the previous example that I'm putting blue over, is when both of the binomials are the same. So that's why it's okay to leave the answer as sine v plus 1 over tangent v. Okay, now we're ready for objective 2, which is to establish an identity. Alright guys, if you get overwhelmed, stop the video, try it out yourself and see what happens. Okay, so establish identity sine squared of negative theta plus cosine squared of negative theta equals 1. Okay, the Pythagorean identity is sine squared theta plus cosine squared theta equals 1. So as long as your thetas are the same, you can use Pythagorean identity. Notice that these are the same. Okay? So if I use a Pythagorean identity and I'm working just on the left-hand side, I can substitute in sine squared theta plus cosine squared theta equals. Okay, so I know that I'm working on the left-hand side only, that this is equivalent to 1 because of the Pythagorean identity. Now I have 1 equals 1, so I have done the identity and showed that the left-hand side equals the right-hand side. When you do these identities, you're going to start on the harder of the two sides, and you're going to work only on that side. It's not an equation, so you don't move things from one side to the other. It's not like that. If you start on the left-hand side, you stay on the left-hand side. If you start on the right-hand side, you're going to stay on the right-hand side, and it's going to require you to do a lot of substitution. So let's go ahead and do the next one. Establish identity. 1 plus tangent u over 1 plus cotangent u equals tangent u. Now this side that I just put a box around, the left-hand side, is the harder side. Okay? I can't do anything with the right-hand side besides turn it into sine over cosine, and that's not going to help me. Because remember, I want to take the left-hand side and make it look like the right-hand side. So our goal is to make the left-hand side, by doing something to it, equal the right-hand side. Okay, so what I'm going to try here, and I don't know if it's going to work, and that's what happens sometimes, but I'm going to try to take the conjugate on the left-hand side to see what happens. And I'm going to try to do the conjugate of 1 plus tangent squared in the numerator. So let's see what happens. The conjugate of 1 plus tangent squared is 1 minus tangent. When I said squared, I meant to say u, tangent u. Okay, the denominator was 1 plus cotangent u, and now I have 1 minus tangent u over 1 minus tangent u. Okay, let's see what happens. In the numerator, it's going to turn into the difference of perfect squares. How do I know that? Because I multiply the conjugate. So I take the first term, I square it, minus the last term squared. So this becomes 1 minus tangent u squared. Okay. In the denominator, I have 1 plus cotangent u times 1 minus tangent u. And you're going to have to FOIL that out, because there isn't any shortcut for it. So 1 times 1 is 1, and then 1 times negative tangent is negative tangent u, and then 1 times cotangent u is cotangent u, and then we get plus cotangent u times tangent u, and this should actually be a negative, so let's go ahead and fix that, because a negative times a positive is a negative. Okay. Alright, I know cotangent times tangent is going to give me 1. So now I have 1 minus tangent u squared over 1, and this is going to be 1 minus tangent u plus cotangent u minus 1, because when I multiply these together I get 1. So the 1's cancel each other. So now I have 1 minus tangent u squared over negative tangent u plus cotangent u. Okay, I'm going to try to keep on working this. This is getting a little bit crazy here, so I don't know if it's going to work or not. I don't think we're getting close. If you check it out, we're not getting close to tangent u. So my approach didn't work very well, and I wanted to show you what happens when that happens. So what I'm going to do is I'm going to erase this, because this is getting too much, and there's only a couple things left I can possibly do. So you start from the very beginning. Happens. So let me go ahead and erase this, and you start it over again. Okay, so the moral of the story is that if at first you don't succeed, you try again. Okay, this time around, I'm going to rewrite the left-hand side in terms of sines and cosines. So I get 1 plus sine u over cosine u over 1 plus cosine u over sine u. So let's see what happens when I do this. I gotta find a common denominator. So in the numerator, the LCD is cosine u. So I get cosine u over cosine u, that's what 1 equals, with a common denominator, plus sine u over cosine u. Okay, now that I have a common denominator, I can write this up as cosine u plus sine u. Okay, let's work in the denominator here. The LCD here is sine u. So I get sine u over sine u plus cosine u over sine u. And let's see what happens. I get sine u plus cosine u all over sine u. Okay, now remember, this is a complex fraction. I'm going to go ahead and draw the main division sign. So what I'm going to do is reciprocate the denominator. So this becomes cosine u plus sine u all over cosine u times sine u over sine u plus cosine u. Okay, because addition is commutative, I can change the order and still have the same thing. So cosine u plus sine u is the same thing as sine u plus cosine u. all we've done is change the order. So I can go ahead and cancel those two binomials out. And when I do that, I get sine u over cosine u. Okay, we're getting somewhere because by definition, sine over cosine is tangent u. So now I took the left-hand side, and now I have the right. So once again, that was an example of, oh, no, it doesn't work the first time. So what do? I erase and start from the beginning and see if I can do something else. Alright, that's the end of 8.4, part 1.